Okay, cool. So recursion. So recursion is like one of those things that you hear a lot about, and it's probably one of the first topics that intuitively is hard for like humans to reason about. And the reason why I say that is just because it's like humans are used to doing things in a very linear fashion, right? Like I do this, I know what I'm gonna do next, and I know how I'm gonna keep doing it until I reach a certain point and then I stop, right? One of the things with recursion that makes it really tricky to conceptualize is inherent within recursion is this idea that you use recursion because you actually don't know how many times you'll do it and when you'll stop. And in recursion, what the tricky part of it really is that like each time that you do it, you're actually not quote unquote doing it once and then moving on to the next thing, right? You actually don't know where you'll end up after that step. It's taking a while. Fine. All right, this doesn't work. I'm just going to zoom up the screen, and we can just do it that way. All right, cool. So when we talk about recursion, the most fundamental way that everyone describes it, for better or worse, is a recursive function is a function that calls itself. Okay, and that doesn't really help us that much if we think about like kind of like how the function that we've seen so far today, right? All those functions they pretty much do what? They define it, and then someone calls it. The function executes, and then we move on, right? It's a very set pattern of like it's very easy to very linearly see where the function starts, where it goes, and where it ends up. Recursion is a little bit out of the norm in the respect that the function actually, in some cases, will call itself. And really, that's what defines a recursive function, is that if anywhere in this function, if a certain condition is met, then this function will call itself. That defines recursion, because you're potentially recursively calling yourself over and over again. However, that just means that the most important part of any recursive function is what we call the base case. And the base case is just essentially tells us, hey, when should we stop calling ourselves? Okay, if you write a function that calls itself over and over again without stopping, you'll actually get the same exact error that happens when you try to iterate a for loop without incrementing the counter. You'll get something called a stack overflow or a memory leak, or basically something that basically is the computer trying to tell you, hey, I try to do this a lot of times, and it feels like there's no end to it, and I'm gonna stop right here. Otherwise, I'm gonna actually use up all my memory and break down. Okay, so in a recursive function, the one thing that you always want to be very, very clear on before you even start writing any code is what's my base case? Like, at what point should this function stop running? Okay, so looking at the function on the left, it's a countdown function, right? And all we're really doing is we're counting down numbers. And so when we look at this function, once we pass in a number, the first thing we do is we log out the number. And then we have an if statement that says if the number is greater than 0, then we call this function with a number, but we subtract 1, right? So in this case, what's our base case scenario here?
N equals 0.
Right. The base case is basically anything that happens is because in this if scenario, we're always calling ourselves, or we're always calling countdown again. So our base case is actually down here is in this else statement. And what this says is basically once we reach the else statement, it means we just log something and we're done. And how do we reach that else statement? We reach it when when n does not meet this condition. So when n is not greater than 0. So it could be 0, it could be -1, it could be any number less than 0. But the base case here, when we look at this, and it's not quite clear immediately, but basically the base case here is whenever this else statement is met, that's when we stop. Okay? If we had another countdown, for example, inside this else statement, then this function is going to break. Because what's going to happen is it's going to keep running over and over again, and there will be no scenario in which we don't call ourselves. So what happens is we end up calling ourselves hundreds and thousands of times in quick succession. And usually at that point, most modern computers will throw an error and tell you that you're doing something wrong. Okay? So the base case is actually super important. And for any workshop tonight that you work on, one of the downsides of practicing recursion is that you will most likely definitely get caught up in some infinite loops, and repo will probably pause or break, and so you probably need to restart your browser to get out of it in some cases. So before you run any code, always just be very clear with yourself what your base case is, or either when are you telling the function that it should stop executing itself. Okay? Sorry. So recursion is, as the title indicates, it's an alternative to iteration. And what that means is that if we look on this function on the far right, we're very familiar with how this works, right? As we say, hey, var I equals n, we increment the counter, and for everything in this, for every, I guess in this case, while basically for every number of n, we log it out, and then at the end of it, we log out a message, right? Like this for loop is something that we're very, very familiar with because we're saying, here's a number, go through it X number of times, and when I look at the for loop, it's very clear where it starts and where it ends, right? When we look at the recursive function we just did earlier, it does, the output is going to look almost the exact same, right? The only difference is here we're defining very clearly iteratively, hey, we're benchmarking against I is an increment by this much, and we're going to stop once we violate this middle condition here. That's how a for loop is constructed, right? In a recursive function, in this case, we actually don't know what the end case is before we call it, right? Like if I blocked out like this function, right? If I blocked out this else statement, right? And we just saw these first 4 lines of code, and all we're seeing is we have a countdown recursively function, we have a console log, and then we say, hey, call this function on your self -1. And that's it, right? We actually don't know how much longer this could potentially go on, right? Because for example, we actually don't know if there's anything else going on outside of this function that could potentially be incrementing the number somewhere else, right? So because of that, one way to think about a recursive function is that it is like a for loop, except the endpoint is like you don't actually know kind of where the default conditions going to be triggered from the outside looking in. So in this case here, we can look at this for loop and say, if we go through it linearly, we know that this is going to end right here. For that function to the left, we can probably assume at the end of the day that yeah, when n is greater than 0, at some point we're going to reach our base condition. But not all recursive functions will be structured in that manner, where it's very clearly where like how many loops you're going through, right? In this case, I can tell you that looking at this for loop, I'm going to go through it n times. With recursive loops, you can't always make that assumption. And in fact, a lot of recursive loops are designed so that you keep going until you hit something, right? So if I was to say, hey, roll a die until you get a 6, right? I have no idea how many times that function is going to run, right? But it's going to stop once it's a 6. But that could be the first time, it could be 1,000 times. And so with recursion, the other thing to be aware of is when you run a recursion with one input versus running it with another input, the results can vary dramatically, and you actually, in most cases, don't know how many times exactly something's going to take. Okay, but in this example here, this is a good comparison of just kind of how you would do things recursively versus doing things iteratively. I think for everything that you can do iteratively, you can probably do recursively, but the converse of that is not true, right? So if I am rolling a die and I'm trying to get a 6, I can't really represent that with the for loop. However, what can I represent that with that would be very similar to a recursive function? A while loop, right? So basically, while this condition is not met, don't do it or do something else, right? Okay, so recursion works because of synchronicity, okay? And what synchronicity is telling us is that it's kind of like right now when we execute a line of code, right? We kind of take it for granted that line 1 is going to execute first, then line 2, then line 3, and so on until we reach the very end of the code, and then we stop, right? And we're going to actually rely on that quite heavily in this case because of the fact that when we call a recursive function, what's happening is we're actually going to be calling different instances of the same function. So the way, and I know I didn't go over the text on the bottom, but a lot of that's going to come through here is the way that we think about how this all works is through something called a call stack. Okay, let me grab the whiteboard really quick and I'll kind of diagram out a way to make our recursion that I think is pretty helpful. 1 second. Okay, so one of the ways that people talk about the call stack very often is it's like a stack of plates, right? Like when you go to a cafeteria, you're gonna have a stack of trays right there, right? And everyone who wants food is gonna come grab a tray. In most cases, you grab the tray on the very top, right? You don't go to the. I mean, I guess you could theoretically, but most people, like I guess for courtesy or otherwise, you grab the tray on the very top, right? And so if I grab the first tray, the person actually is going to grab the new first tray, right? So if I have, for example, if this is like my baseline, right? And these are all plates. If the first one that comes grabs this top plate, right? And so then this top plate goes away. And then the next person that comes grabs this new top plate, and this plate goes away. And then finally, the third person is going to come and grab this plate. This one, okay? So obviously, very simple example, but that's how things are, I guess, popped out. Or in this case, we'll say the word used, but in computers we talk about like kind of finishing or popping. Okay? So that's how we take things off the stack, right? We take them off the very top. However, if I was working at a cafeteria and I wanted to put plates on here, assuming I was cleaning them one plate at a time, and I had to put them on the stack, I will also start at the very bottom, right? I would say, okay, I finished cleaning my first plate, I'll put it at the very bottom. And then I finished cleaning my second plate, I'll put it right on top of that, and so on and so forth. And so once again, if someone was to come and take a plate off, they will be taking the most recently cleaned plate. Okay? I know, very juvenile and very simple, but this is super important for understanding how we're doing. Okay? So in this system, there's like in computer science, there's something called like first in, first out, right? Or last in, last out. And so what this really means is this plate. If I'm cleaning the plate, I'm putting it on the stack, right? That's called going in. Okay. In this case, the first plate that goes in the stack is the last one out, right? And the last plate that gets put on the stack is the first one that goes out. Okay. So this first in, last out concept is super important for understanding recursion. And why does this present a very good way of modeling recursion? It's because if I call a function 5 times, right, what I'm really doing is, if I call it the first time, this is call 1. Let me just do a C1. This is call 1. And then if call 1 calls this function, calls itself again, what that does is it calls the function again, but now it calls it call 2, and now call 2 goes on top of call 1. From a computer standpoint, what that means is, before I finish up with call 1, I have to finish with call 2 first, right? I can't get to the very bottom plate without taking the one on top of it off first. And if call 2 calls itself, so now I have 3 iterations of the function running, call 3 then goes on top of call 2. And so now, if I'm a computer and I look at this stack, I can't just pick and choose which one I want to solve first. By definition, because of synchronicity, I have to say, let me resolve call 3 first. Then and then once call 3 is resolved, I can finally do this, and I'll go to call 2. And then once call 2 is resolved, then I'll go to call 1 and finish that. I have to do it in this order because that's the order in which these functions were called, and I can't just jump around. I have to do them in a very synchronous order. The order in which they're called has to be the order in which they are resolved. Okay? So without putting any functions in there, does this concept make sense of us putting something into it and how we get it out, right? First in, last out. The first thing that we put in will always be the last thing that's resolved, right? So when we talk about a recursive function now, so if we look at this function out here, there's say hello, there's wait for response, there's say how are you, and there's meet me, right? There's 4 different functions here. At the very end of it, down here at the very bottom, so line numbers are good, we call meet me, right? And so what does that tell me? That says, okay, at the very bottom here, the first function that we call is going to be meet me. Okay, right? The first thing we call down here. What does meet me do? Meet me is a function. When we execute it, we then call say hello. So this tells me that I'm now triggering another function call right here. That's called say hello. And then let's see what say hello does, right? I'm not going to say how are you yet, right? Because once again, this say hello has to finish resolving before I move to the next line of code. So what does say hello do? Say hello goes and says console log out hello. Okay, so assuming this is my console log here, the first thing that I'm gonna log out is gonna be a hello. And more importantly, after say hello logs out hello, it finishes, right? This function is done. So in essence, I've resolved this say hello function. So now I can take this say hello function off my stack. And now I'm back to meet me, right? I'm back to meet me. I finished this line here, and now I'm gonna call say hey how are you, okay? So now by calling that function, I basically put another plate on top of the stack, and I'll just call it how are you. Right? So now we have another function on top of the stack called how are you. And when we go to how are you, what it does is it actually calls something called wait for response. So we're not logged this out just yet, because once again, how are you calls for something called wait for response. And I'll call it here, it's just wait. And before we move on any further to how are you, we have to resolve wait first. What does wait do? Wait console logs out waiting. So this meet me called how are you,
Yeah, right. Okay.
and then how are you called wait for response.
Yeah,
Right. And so now wait for response is finished, right? It's gone through the entire function, it's executed every line of code, and we're done. So now I can take wait off my call stack. And where did that leave me? Well, it seemed like I was in the middle of the how are you function. So now I go back to how are you. I finished up resolving wait for response, and the next log is how are you. And once it logs out how are you, this is done as well. And then finally we go back to the meet me and say, oh great, now we're also done with meet me too. And so we're going to take this off our stack. And then now we're actually finally done with this function, right? We've gone through it, we call it every single function, we've gone through every line, and we had to do it in order, right? The biggest thing about all this is you cannot move on to the next line of code until you resolve the current line you're on. Okay, that's just like super important, and it's a very fundamental part of how like JavaScript works. So it's hello, waiting, how are you, and then we're actually finished. Does that make sense? The order in which we did everything? Okay. The most important thing is when you see this, assume that this is happening synchronously, which always means say hello has to resolve before you do it. You very rarely are going to be an opportunity where you're going to be executing two functions in parallel, unless you make one of them asynchronous. Okay. So writing a recursive function, right? Once again, most important thing of writing a recursive function is to define the base case, right? When should I stop? And the base case has to be something that has to be met eventually, okay? In most computers, it's really hard for them to check because like if I say something like roll a die, right, X number of times, theoretically it could run like a million times before I get a 6. It's not a problem, right? So computers can't really check for a base case for you. In most cases, what they'll do is they'll run it like a few 100,000 times, and they'll probably throw an error at you if after a few 100,000 loops it's still going, because they're going to assume that hey, this is not intentional, and clearly there's something going on here that shouldn't be happening. Okay. So after you've established your base case, which is when to stop, then obviously the flip side of that is say, great, when should I keep going, right? When should I call myself? And then in the second stage here, when you say when should I call itself, you also need to define something that understands that, okay, when I call myself, what am I doing differently, or what's changed from me calling myself from me calling myself this time than when I was called last time. And I think the best way to do that is looking at an example, right? So let's take a look at the factorial example. So this function here is factorial, right? And we're basically taking a number, and we say if the number is 1, then we return 1. Otherwise, we return n multiplied by calling itself recursively factorial of n minus 1. Okay, so let's step through this kind of as a group around how this would actually look if we did factorial of 5. So I'm just going to call this factorial, and then if n is equal is n multiplied by factorial. Okay. Handwriting's not nearly as good, but I'm just copying down line for line what was on here. Okay, same thing. If n equals 0, we return 1, otherwise we return n below by the factor of 1. Okay, and so here, assuming we had a, I'll make this now my call stack. When we call factorial of 5, the first thing we're doing is we're basically saying, okay, let's start with my base function, okay? It's the factorial of what? 5. So I'll just do f of 5 for short, okay? This is what I'm calling. When n equals 5, I go down here. Does n equal 0? It doesn't, right? So what happens? So then we return 5, let's start with Winston, right? 5 multiplied by the factorial of what? Factorial of 4. Okay? Even though I'm on last line, I haven't finished resolving this last line yet, right? Remember, I'm not done with the function, though. I've resolved every single line and reached a logical conclusion. So in this case, we haven't reached the endpoint yet because I still need to evaluate what factorial 4 is, right? And so what that does is, imagine if this was like the first time we called it, if this was like fn of 5, so say fn of 5, we're now going to trigger another call here. And this function is going to be fn of 4. Okay? And so here we're going to add one more to the call stack. It's, hey, before we resolve fn of 5, we need to resolve fn of 4 first. Okay? So how does fn of 4 work? Well, let's just go through logic here, right? Is 4 equal to 0? It's not. So we're going to return what? We're going to return back 4 multiplied by what? Not 3. Factorial 3. Right? Because it was just 3 that I've done, that function. Right? Factorial 3. Okay, great. So am I done with fn of 4 yet? Why not?
Let's go to 3.
Right, because now we need to add one more to our call so I can say, okay, well, before I can resolve 5, I need to resolve factorial 4. And before I resolve 4, I need to resolve factorial 3. Okay? So, bear with me, sorry, for the non-sequential order. But now, for fn of 3 now, we do the same as x does, right? It doesn't equal 0, so we're not going to return 1. What are we returning? We're returning 3 multiplied by the factorial, so write FAC, of 2. Okay? So, we're not done yet because obviously factorial of 2 is not like a number, right? It's a function that we're calling. So we need to invoke another function where we call 2. Okay? So we go down here now and we say f of 2 and we return 2 multiplied by factorial of 1. Okay? And so are we done with 2 yet? No, because we still have to call it one more time for factorial of 1. But when we call factorial of 1 now, let's call here, and for fn of 1, what happens? Sorry, 2 more times. We do the same thing again, my bad. We do return of 1 multiplied by factorial of 0. Now we have fn of 0, okay? So notice how our call stack gets bigger and bigger, right? And we're actually calling, I guess, this 6 times, okay? This is why the first and last out is so important, right? We can't just pick and choose any of these to resolve, right? We have to resolve whatever's top of mind right now. And whatever's top of our call stack right now. And f0 is our latest at top of our call stack, right? Because everything else depends on it, right? So finally, when I go here and I look at fn of 0, what do I get? What do I return? 1, right? Each of these is this function. So when n equals 0, I return 1. Notice how when I return this 1, I exit the entire function block, right? That's why this line is never triggered, right? Remember, returns gets you out of the nearest function scope, okay? Yeah. So this returns 1. Well, great. This returns 1. So that means I've now finished up with this fn of 0, right? I can cross this off my list. And then that just means, hey, I know what this is now. This is now going to be 1. And I'm returning back 1 multiplied by 1, which means what? I've also finished up my fn of 1 function, right? Like we just did this as well. And I know that fn of 1 is going to give me 1. So here, when I do give me factorial 1, this is going to become a 1. And now I'm just returning 2 multiplied by 1, which also means I've done with my fn of 2 block, right? And so on and so forth. And so here, I can replace all my factorials of 2 with the number 2 itself. And when I'm returning back 2 multiplied by 3, I'm actually done with fn of 3 as well, because I'm going to return this to a 6. Okay? Fn of 4 becomes returning 4 multiplied by 6, so that's 24. So we're actually done with this as well. And finally, we go back to the very beginning where we're multiplying by the factorial of 4, and we can say, hey, we're 24, and if we return 5 times 24, we get 120, and we're done with this fn of 5, and we get our final answer of 120. Okay, so that's like structurally how a recursive function looks, right? Is that every time you call it, you're creating a new instance of that function that's going to run. Okay, so when we call it factorial 5, means we need to call factorial 4. One of the really hard things about assuming we didn't do all of this, if you're just looking at this, sometimes as people really, it's hard to look through it and imagine 5 different iterations of this running concurrently. So if it helps you think about it, like blow it out each time, so you can almost treat them as very distinct functions, right? Like whatever happens here wouldn't impact here, right? Because it's not like we're going through the same code, but what we're doing is we're calling each function individually. Okay. Also very important, the call stack, right? Because in this case, each time we need to finish the entire function before we return the value. It just means we kept calling up more and more things on the call stack. And so, in an instance where you have a poorly defined base case, where you don't tell it when to stop, what happens to the computer is that stack is going to grow infinitely long, and at some point, you're going to trigger a warning to the computer saying, hey, look, this call stack is getting out of control. I'm going to assume you didn't want to do this like a million times in a row. I'm going to shut you off here and have you go back and try again. Make sense? Yes?
Yes.
Good?
Yes.
It always makes sense when, like, I guess, you look at it on a whiteboard, I guarantee you. But when you start doing it, it's going to get a lot trickier. Cool. So here, this is doing the same, right? Like, this is basically a layout of what we just did, right? Which is to say that, here, right? We call this 6 times in a row, right? And we finally reached our base case, which, by the way, how do we know this is the base case, or what's our base case here? It's return 1. And the reason why we know this is the base case is because in every other scenario, i.e. when n equals 0, we actually call ourselves again, right? So when I look at your code, or when you look at your code, really, you always should be able to say, hey, this function should stop at this point, and there's a viable path towards getting to this point. In this case, the viable path is if I have a number and I keep subtracting 1 from it, at some point it's going to become 0, and that's when it stops. Right? So like that makes sense to a computer in terms of like, that would make sense to a human understanding. Okay, I'm going to keep going until I reach a certain scenario, and I understand how to reach that scenario. Right? It's why something like rolling a dice until you get 6 is risky, right? Because you could theoretically never reach that point. And so the way around that is sometimes people do like certain guardrails around it to say, hey, only try this X number of times, or if the memory exceeds this, stop, or or some other condition, right? So one of the projects one of my friends did for a job interview, which we, for better or worse, worked on together, was basically like they gave you a Wikipedia page link, right? And the question was, hey, how many clicks is it going to take for you to get from this page to like this other page, right? And the way you do that is you recursively just click on every single link on the page, and then you click on every single link on that page, and then you click on every single link on that page over and over again until at some point you hit that final page's link, right? That's incredibly expensive, and even though Wikipedia is very well linked, like theoretically you could not get there unless you cover maybe millions and millions of pages, right? So like there are real world applications for these kind of problems, and so it's not often as simple as, hey, let me just brute force it, let me just run it as many times as I need to get to the result. Sometimes you need to be a little more careful, a little more clever around what parameters you want to set, so you don't kind of get into a scenario where you're clicking through everything, or you're recursively calling something that's maybe unreasonable. That's basically unreasonable. So we do this math here, we go back, and finally we go back and we get our final result of 120. Okay, oh, sorry, last slide. And then you guys can start in the workshop. So last slide. Once again, I cannot stress this enough, right? Recursion, not a very long lecture because it's theoretically not a very hard concept, right? Like, we can walk through it and we look at it very slowly, it makes sense, right? But the few things that can make your life a lot easier when you work through with recursion, once again, always, always, always specify your base case first, right? You should never go into a recursion thinking, oh, like, this will eventually stop, I hope, because that's how you really get in a lot of trouble. Secondly, testing recursive functions, right? Here we're trying to do a factorial of 5. Was it like long? It was long, but not terribly long, right? If your teacher gave you an assignment to say, hey, you know, like, find me the factorial of 120, you probably don't want to test with 120 to see if your factorial function works, right? You want to test a number like 4 or 5 because then you can kind of step through and see what's going on. If you test with 120, if it does break, it's going to break in a very spectacular fashion. Okay, so for testing recursive functions, always try to start with something that you know is going to do it in the way that you can kind of physically understand it, right? The other thing we test, always test your base case, right? Like over there, I'm basically saying my base case is when it equals 0. So my first test is going to be, hey, if I pass in 0 for n, does it actually stop? If it doesn't, then nothing else I do matters, because if my base case is busted, then my recursive function doesn't break no matter what other inputs or other things I put around it. Okay? Secondly, most recursive functions can be thought of in some ways in an iterative fashion, right? Either with a for loop or with a while loop. Okay, so if you're having trouble visualizing how a function looks recursively, try doing it in another approach first, using a different loop, and see if that at least helps you conceptually understand what's happening behind the scenes, and then you can start to identify the patterns of kind of when should I call myself or when should I be using myself. Okay. Third, draw it out, like do what I did, right? Like blow it out, like draw it on the paper so you can clearly see what's happening at each stage. Looking at the computer screen and trying to visualize each runs of it, it's not impossible, but I think when you start off, it's definitely a lot more difficult than it is to draw it on paper, because after a while, mentally you lose track of which iteration you're on or what the variables are, and it's hard to kind of get that back sometimes. So having it on pen and paper definitely helps, especially for the smaller loops. Okay. And then lastly, today's workshop is going to be pretty difficult because this is something that's like it's easy to see me do it on the whiteboard because I've done it and because we can step through it very logic together. But this is like a whole new way of thinking about functions, right? Like really up until now, you've always, whenever you call it a function, you've known how it was going to go. And now for the first time, you can think about, okay, is there a way I'm going to call myself? And more importantly is, hey, when I call myself, am I going to get back the right values, right? Notice how in this example we did here, right? We're basically relying on this return statement to give us back the basically capture the sum, right? So if you think about kind of how our computers calculate this, like we're calculating almost everything like in memory, right? Like we're never saying, hey, do this, store the value, do this, store the value, do this, store the value, and then let's all multiply together at the very end. We're saying, hey, do this, which requires you to kind of do this in the same memory, which requires you to do this in the same memory, and so on and so forth, right? So one of the trickiest things about recursion, especially from what I've seen from the sessions, is that like people kind of they forget that, hey, executing this function is fine, but you need some way of returning it back to the person who called it, right? So in this case, for factorial 4, we call factorial 3, right? But what does that mean? It means we need factorial 3 to actually return something back to factorial 4. If we just call factorial 3, that's all fine and dandy. But then here, this is going to multiply 4 multiplied by whatever factorial 3 returns, right? And if you don't return anything, you're going to get back undefined, and this is going to error out. Okay. So the other thing, the other pothole, I guess, I can bore you guys again, is when you look at a recursive function, always be very careful about what you're returning, because the return statement sometimes is like, in some cases, even harder than the base case to determine, because depending on kind of what you're doing, it might not be quite as clear intuitively what you want to get back from your from each run of the code. Okay, so any questions on recursion before you guys get started? Yes.
So the base case should be first, right? When we're building. Is
Um,
that a good practice?
In most cases, I would say yes. Like if you remember, like in the countdown function we saw the very first, it had an else statement, which is fine. So it doesn't need to be sequentially be first. But I would say like for practice purposes, like if you could make your base case very explicitly with the first thing that you see, that would probably be a good catch. The other reason why sometimes you want to put it first is kind of like the way we have the return statement structure there is that like, hey, if it hits the base case, nothing else really matters, right? So if we do like an else statement, like in that one we did it like an if statement, which was like let me go back here. So in this function here, right, we say, if this, then do this, else you reach your base case. On line 1, we could also, or line 2, after this console log, we could very well easily have said, if n is equal to 0, console log, I'm done, and then just put this down on the line after. So we don't even need the if else statement. If that makes sense. Right? So putting it atop has a practical use, but for practice purposes, I would say yes, it's definitely better to see it kind of in a more clearly defined manner. Yes.
How would you decide between using this and a while?
So the while loop is something that's so in practice, what I've seen is that most recursive functions can be written in a while loop in a certain way. The only thing that the while loop doesn't do as well is that in a while loop, if you remember, like while basically takes in an expression, right, and it evaluates it to either be true or false, right? Recursion gives you a lot more flexibility in determining your base case. So like that's like probably and obviously for all of these, you can probably figure out some crafty way of converting into a Boolean. In which case you could do it in a while loop as well. So like structurally speaking, like if you work hard enough, you should be able to do both in either case. But doing something recursively, is actually a lot cleaner, believe it or not, right? So if you go back to the example I had earlier of like clicking through Wikipedia pages, like if we do that in a while loop, I guess we could. We could have a flag that says, hey, if I find this page, do this. If not, do that. But when I write it out, it's going to look very messy, and it's not going to be nearly as clear as to kind of how I'm looping over it. And so in that case, recursion just looks better. But from a fundamentally structural standpoint, you could do most things you do with the recursive loop with a while loop.
Well, that's kind of disappointing.
I mean,
yeah. Did you end up for your Wikipedia thing? Did you end up using a recursive function because you had no other way? Or?
We ended up using a recursive function because it was like it just made the most sense, right? Like I'm gonna keep looking at this thing until I find it. I'm gonna keep clicking every link in order until I find it. And the reason why recursion also works out really well is I wonder if
There must be some kind of problem that you can't solve any other way, right?
yeah, I mean like so let's take this factorial example for example. This factorial problem for example, right? Like there's two kind of things, right? The while is going to evaluate this, right? But in terms of how do we keep track of what our total product has been thus far, we could have a variable in the parent that we pass into it, and we just tweak that parent variable. So it's not impossible to do, but it's just not very clean. And so what I mean by that is, if we were to write this out in a while loop, we could do something like while n is equal to what n does not equal to 0. Right. And then we could say, and then here we got something called var total. So it goes 1, and then we say total star equals by n, and then we do like n minus, right? So like this is like theoretically doable, but it also requires us to have a kind of a global or a parent variable or a global variable for for us to be able to treat things with. So like I guess like in some cases if you don't have that luxury, you would have to use recursion, because recursion allows you kind of like recursion. Recursion returns things in a way that whiles can't, I guess, unless you keep track of it with a global variable.
That's not the best example because that's, I mean, it seems like if you're, there are far easier ways to manufacture oil. I'm just asking like what kind of problems can you not, can you actually not solve it anyway?
Yeah, I can look it up, but off the top of my head, like the ones that you guys were using most today, I think all of them can be done with a while loop. But I think fundamentally, like it's like the principle of recursion that's like calling a function, like calling functions is like it's super hard. And I say that as someone who like I thought I knew what functions were, and I started working and started using a lot of functions, and like the calls get really crazy and they get called in kind of unconventional ways. And so like even just getting familiar with understanding how to call yourself over and over again is like very critical. So for now, I guess for the benefit of like learning about recursion, I would try to use recursive loops in your solution. Down the road, kind of like yesterday, right? Like we learned a bunch of array methods, and if you hated them, you don't have to ever use them ever again, right? You can do them with a for loop, you can do them in other ways. But for now, just to make sure that you're like up to speed on these concepts, I would strongly encourage you to use recursion for the problems for tonight.
Sure.
Cool. Any other questions about recursion? Okay, awesome. So take a break. I will get the pairs out to you guys, and then we can get started.